Hey everybody, welcome back to another wonderful week of Trig Pre-Calc. Here's your do now, it's on the flip chart, feel free to do it. These first five you really should try to do without a calculator. However, I know some of you are extremely reliant on your calculators, so in this section it's okay to use your calculator for those, but again, if you're planning on taking calculus next year, you should be able to do these by hand, definitely. Here are the answers. They're also on the flip chart, so just note some things here. 1 is 1, 2, 5, 3, 3/2, blah, 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 4, 2, 5, root 3 over 2. If you didn't know how to do those, unit circle, guys. Use your unit circle. Graphing, note that number 6 is in the first quadrant, 7 is in the fourth quadrant, 8 in fourth quadrant as well, and then 9 right on that, what's it called, y-axis right there. Completely blanked on that one. Okay, assignment, that was last week. But now we get into the fun thing, and I really do think this is fun. You get some really cool graphs when you talk about graphs of polar functions here. I guess we're saying graphs of polar equations because we don't want to mess with you guys on your whole function, but really we could call them polar functions. We will begin graphing polar equations using a tool that we've used since graphs were first introduced so many years ago, a table of values. What I do need to point out to you guys, the traditional way that we use polar equations is that r is the dependent variable and theta is the independent variable, which kind of really messes with me personally when I talk about the ordered pair being r comma theta. I mean, we're just used to the independent variable being first and the dependent variable being second, but hey, we don't get to make this stuff up. We're just going off of somebody else's work here, so we have to follow their standards. Now, I do want to point out here, what we are doing here, we are saying the distance from the pole is a function of the angle created from the polar axis. There is actually a nice little tool out there. It's called this right here, Spirograph. This toy right here is actually a polar grapher. And let me just open it up here. I've actually got a couple of pieces of the Spirograph out already because they stick in there kind of. But you can see you've got an outer gear and you've got an inner gear. You've got many different sizes of inner gears. And what I can do, whoa, whole camera setup just started falling over there. I'm sorry, guys. You okay? Any motion sickness in the back there? Okay, so what you can do here is you can just put your circle down wherever the dang you want to, and let's just say we're going to start at the polar axis here, and I just put my pencil, or well, pen so that you guys can see it a little bit better, in one of those circles, and as I rotate through here, I get a different radius for every rotation that I go around this circle. And it ends up, you get some like really cool designs on here. And eventually it loops back onto itself and you just start making the same shape over and over again. You can see all of these designs on the front. They were made using a spirograph. There's actually an instruction manual that you can use for it. I get kind of geeky with it and just like make some really fun. It's just fun to play with. It's really toys. Toys, that's what makes life important, right? But we are not trying to play with the toys. We are trying to figure out how to do this mathematically. So, mathematically, we have to use what we learned from last class. Graphing. Alright, so we've got setting up a table of values. I like to set them up horizontally, and just to keep things straight, I put r on top and theta on the bottom. But you may be aware that when we make a table of values, we get to choose what our independent variable is, and then the dependent variable depends on the independent variable. So what I'm trying to say here is we're just going to make some stuff up for theta. We just choose whatever numbers are good for us. Now, I will point out the numbers 1, 2, 3 are not easy numbers when we talk about these types of functions. We see sine of theta. I happen to know that 0 is an easy number to deal with there, because I know that sine of 0, and I'm just going to sketch the unit circle at the top here. Unit circle, I know 0 is right here, and I know that that ordered pair is 1, comma 0. So sine of 0 is 0. You could use your calculator to verify that if you want to, or just trust me here. 0 times 2 gives me 0. So at a rotation of 0, the radius is 0. So the first point on this mysterious figure that I don't know what I'm drawing yet is going to be right on the origin because the radius is 0. You guys saw some of those graphs last week that whenever the radius is 0, it's right on the origin. Now we choose the next point. That would be easy to evaluate with sine of x. And I'm just looking up here, again, unit circle. I know there's 3 points here. I know that at pi over 6, I've got root 3 over 2, comma 1/2. Again, I'm just producing the unit circle from the top of my head here. So I can see at pi over 6, up here, I've got 2 times sine of pi over 6. Sine of pi over 6 is 1/2. I've got 2 times 1/2, which is equal to 1. So here, I'm going to go to pi over 6, which I believe, looking here, 1, 2, 3, 4, 5, 6, yeah. So the second striation here is going to be pi over 6. And I don't feel like scaling anything out, so I'm just going to say that the first circle, no, let's scale it out. Let's make this 1. 2 circles to 1, 4 circles to 2, 6 circles to 3. All right, so at pi over 6, I'm on the first circle. Okay, cool. I can't see anything of what's going on here. It could like make some sort of sine wave. Really no clue, so I'm just going to keep making up more points. So I've got pi over 4. Pi over 4, remember pi over 4 on the unit circle, we've got root 2 over 2, comma root 2 over 2. So this is just going to be root 2. Oh, man, that's going to suck, because I'm going to have to use a calculator to approximate that. At pi over 4, I'm going to have my r value of root 2. It's going to be 1.414. I don't know if you guys can see that quite on my calculator. So at pi over 4, which is halfway through the first quadrant, I'm going to be just before 1.5. So right about there. That looks like 1.4. Okay, we're going to keep going, and we're going to keep just producing stuff. So at pi over 3, these ordered pairs up here are switch-a-doo-doo-dot. So sine of pi over 3 is going to be root 3 over 2 times 2 gives me root 3. And again, here you can use your calculator for it. Oh, hey, look, root 3 is right there, 1.73. So at pi over 3, probably about halfway in between those two circles, in between 1/2 and 2, which is about 1.75. Still can't see what this looks like. Pi over 2. At pi over 2, well, I'm up here. That's going to be 0, comma 1. So sine of pi over 2 is 1 times 2 gives me 2. Okay, cool. We're back to integral values right here. I'm just going to keep going. I'm going to go at pi over 3. Sorry, not pi over 3. 2 pi. Put it in the wrong place. 2 pi over 3 for my theta gives me an r, and that would be at this guy right here. That's the reflection of this line right here. So sine of 2 pi over 3 is root 3 times 2. Sorry, root 3 over 2 times 2 gives me root 3. So it's going to be at the same location here. Put over 2 lines in. 3 pi over 4. I'm going to get a value of 3 pi over 4, gives me root 2 over 2 times 2 gives me root 2, which is that 1.414. So I'm at 3 pi over 4, 1.414, just a little bit before 1.5. And let's round this out. Oh no, we got a couple more. 5 pi over 6. 5 pi over 6, sine of 5 pi over 6 is going to be 1/2 times 2 gives me 1. So at 5 pi over 6, I'm at 1. And last but not least, I've got pi. Sine of pi is 0. 0 times 2 gives me 0. Okay, look at that. I'm at the same point there. Now, how do I know where to stop? You stop when you feel comfortable to stop. My thought process on this one is, since we're talking about sine, we are talking about a periodic function, and we remember that sine has a period of 2 pi. I don't feel like going as in depth with these points right here, so I'm just going to make up like major points here, like maybe 3 pi over 2. I'm thinking it looks similar to this, but now I just want to figure out what radius I'm at down here so I can start like filling it in. Here I've got 3 pi over 2. Sine of 3 pi over 2 is, I believe, -1. Yeah, because it's down here. 0, -1. So -1 times 2 gives me -2. So at 3 pi over 2, oh, look at this. At 3 pi over 2, I'm at -2. So I want to go up to here. What actually happens as we go further and further beyond pi in this one, we just start recopying these points here. Like if I wanted to go at 7 pi over 6, sine of 7 pi over 6 is -1/2. -1/2 times 2 gives me an r value of -2. -1/2 times 2 gives me -1. So at 7 pi over 6, which is this line right over here, I have an r value of -1, which is going to, instead of pointing me out here, I'm going to point out here. So you can see all those points just go over and over and over each other. Now, in order to produce the graph, all I got to do is come up with a smooth curve on this one. And when I smooth this out, it comes out to be some mysterious figure. I don't know what to call this, so I'm just going to make up a name for that. I'm going to call it a circle. All right, spelled C-I-R-C-L-E with a hard C on the beginning. So circle. In case you're not picking up my sarcasm, it's a circle. This is how you make a circle with a radius of 1 straddling the y-axis and going through the origin. Pause for a second, try this one out, and I'll show you what happens with it. I mean, really, if you want to, you can go in here and, oh, whoa, look at that weird stuff on my calculator. Oh, that cool? Okay, yeah, let's clear that out. Clear, clear, clear. Okay, so here, what we could do is we could put in 3 cosine of x. Notice I am back in function mode here. And what I'm going to do, I'm just going to go into my table, and I've got this set up. If you're not in my class, you've never seen me do this before, but if I hit second window, I can change my independent over to ask, and all of a sudden I've got a table of values that's going to produce stuff for me. So like I can put in 0, pi over 6, pi over 4, pi over 3, and again I'm just matching up these lines down here so that I can get good points on here. Pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi, 7 pi over 6, etc., etc., etc. It lets me fill this out a lot faster. So like I know, again, I have this plugged in as 3 cosine of x. I go to my table, I can plug in 0. Okay, 3 pi over 6. It's just auto-populating. Can you guys see that? It's giving me the numbers so easily. 2. Let's call it 60. We don't really need to go that accurate because I can't really measure that accurately on here. Pi over 4. I like to write them down so that I don't forget which one is which. 2.12. Pi over 3. I've got 1.5. Pi over 2. I've got 0. 2 pi over 3. I've got -1.5. And you do this until you feel comfortable, you know what the picture is going to look like. Obviously, I have no idea because it's just points. So I'm going to go up to pi because that was my telltale last time. And then I'm going to graph them and see if I can get a picture on that one. Where I'm at 3 pi over 4. Okay, -2.12. Hey, look at this. it's nice and symmetric on those. Not pretty. 5 pi over 6. I've got negative 2.60 and pi. I probably could have calculated that by hand, but I was feeling a little bit lazy. Okay, so I can see that I'm going from 0 to 3 on here. So I'm going to make every other circle worth 1 unit. So 2 circles 1, 4 circles 2, 6 circles 3. Now I'll just start graphing. Rotation of 0. R of 3. Boom. Pi over 6, 2.6. So 2.6 at pi over 6, the second striation, is going to be a little bit past 2.5. Pi over 3 is going to be exactly at... Oh, pi over 4. I was like, did I not graph, or did I not figure out what pi over 4 was? Okay. At 2.1, a little bit past 2 circles. Nice and clean at pi over 3 of a 1.5. And pi over 2, again, nice and clean. And you can see it actually looks like a semicircle right up there if you connect with a smooth curve. When you're drawing your curves on here, you do want to make sure that you have some sort of smoothness to it. Remember when I used my spirograph, everything came out being nice and smooth. The polar graphing is just all about smoothness here. Let's see, where were we? Pi over 2, so 2 pi over 3, that's this guy right up here, but since my r is negative, it's going to shoot me over into the fourth quadrant. 3 pi over 4 at negative 2.12, so right out about here. 5 pi over 6 at negative 2.6, so this side, but whoosh, all the way across, 2.6. And you can see it looks similar to the last one, except this time instead of straddling the y-axis, it's straddling the x-axis. I put in a couple more points. Let's go 3 pi over 4, 2 pi, just to verify when I have 3 pi, not 3 pi over 4, 3 pi over 2. 3 pi over 4 is in the second quadrant. I want to go down here. 3 pi over 2 gives me 0 again, so that's going to be at this point. 2 pi gives me 3, so it's going to be at this point. It's really just darkening that circle as we do this. So that whole periodicness of the sine function causes you at some point to bust out of what we call a unique domain, and the picture just keeps going over and over and over again, so that really, if you were to graph everything in the domain, which is all real numbers, it would just be that circle over and over and over again. And you can see I did draw it correctly. Now one last one, if you're following along on the flip chart. Oh my gosh, I dropped my pen. It's in a milk crate. Oh no. This is the one that you have. And just to make it a little bit simpler, I mean, I would definitely go for my calculator. 1 minus 2 cosine of x, using x instead of theta because my calculator doesn't understand theta. Again, going to my table, just going to make up some numbers. Let's get all those out of there. Although those are the exact numbers that I'm going to be using. Again, let's not do that. Alright, so here, my theta, let's go 0. Pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. I'm telling you right now, we're going to have to go higher than that. I only know that because I know where this is going, but I'll show it to you on this graph. So here I got 0 for my r, or for my theta. Why do I have these labeled so incorrectly? Theta and r. Ugh. Wait. Why did I scratch them out and do the exact same thing? R up top, theta down below. I think at some point I thought making my table of values the other way was more logical, but no, it is not. 0, negative 1. Pi over 6. Negative 0.7. Let's just go to one significant figure on there. Pi over 4. negative 0.4 pi over 3, 0, pi over 2, 1, 2 pi over 3, 2, 3 pi over 4, 2.4, 5 pi over 6, 2.7, and finally pi. Alright, 3. So I'm just going to graph these real quick. 0, since it looks like the biggest I'm going is 3, 2 circles to 1, 4 circles to 2, 6 circles to 3. So 0, negative 1, no rotation, negative 1 to the left. Pi over 6, negative 0.7. So pi over 6, first line, negative 0.7, goes somewhere, down here. On that second line, it goes right over to here. Alright, cool. Pi over 4, negative 0.4. Pi over 4 middle, negative 0.4, a little bit before 0.5. Pi over 3, 0. Okay, radius is 0, it's on the origin. Pi over 2 at 1. Pi over 2 at 1, so pi over 2 at 1. 2 pi over 3. 2 pi over 3 at 2, so 1, 2. 3 pi over 4 at 2.4. 2.4 a little bit before. Wait, 2.4, not 1.4. A little bit before, 2.5. 5 pi over 6, 2.7. 5 pi over 6, 2.7, so somewhere up here. And finally, I've got pi and 3. Now, I happen to know what this looks like, but if I'm, like, I know I start here and I start connecting them, and I go through the origin, and I come back around, and I'm just, like, trying to make this smooth as possible, just like a nice circular kind of thing. But I can't really see, it kind of looks spirally here, but here's the case where I need to go for more points. Maybe do like a 7 pi over 6, maybe do 3 pi over 4, nope, 5 pi over 4. 3 pi over 4 again is before we get to pi. Let's just start skipping a little bit. 3 pi over 2. 7 pi over 4. 2 pi. Again, I'm just skipping around a little bit because I know that this pattern is going to continue. It's going to go something over here doing stuff again, and eventually I'm going to end up at this point because, again, I have this periodic function up here of cosine. So let's just get some more points on here. 7 pi over 6. 2.7. Oh man, did I put those in the wrong place? I keep doing that. 7 pi over 6 down here, and 5 pi over 4 down here. So 7 pi over 6 is that 2.7. 5 pi over 4. 5 pi over 4. 2.4. 3 pi over 2. Ooh, 1. 7 pi over 4. 7 pi over 4. Negative 0.4. There, we're getting those negatives again. And 2 pi. Syntax error! Oh, you can't put a plus after pi. Negative 1. So again, I got that negativity here. So let's just put some of these down. 7 pi over 6 at 2.7. So right around here. And you can see it's just kind of like reflecting over there. So I'm going to get that circular-ish kind of thing. 5 pi over 4 at 2.4. So a little bit before 2.5. And again, you can see it's reflecting there. 3 pi over 2 at 1. So 3 pi over 2 at 1. 7 pi over 4, that's this guy down here at negative 0.4 is going to be back up a little bit. So there's that negative 0.4. And 2 pi at negative 1. So there it is. It loops up with it again. And chablamo. I've got one of my favorite pictures. This is actually called a Lemniscate curve. And you guys will learn all of those names here in just a minute. What you can see is this is what we call tedious. It's not really fun to graph this by hand. It's not hard if you become proficient at graphing in polar coordinates, which again you should practice a little bit. That's what we did last week. But there is a nice way that we can actually do this, and that is using some things that we did last week, like converting a r and theta into an x coordinate, so I can actually see that I've got x is equal to r cosine of theta, or in this case, I take the function and multiply it by cosine of theta, because r is equal to f of theta. And then the y coordinate would be r sine of theta, where f of theta is equal to sine of theta. And what's nice here is this now becomes a parametric function here. So here I can actually say, to convert this into parametric form, I've got x is equal to my r 2 sine of theta times, and just the quick conversion, cosine of theta. My y is going to be my r 2 sine of theta times sine of theta. And hey, we know how to do that in our calculator. We can go down here into parametric mode, ignore that there's stuff after where it says parametric mode because we're not quite there yet, and we can just go in here and clear out all that stuff from 2 weeks ago. Clear, 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 clear. All right. And I just type this gobbledygook in. 2 sine of, well, in this case, since we're in parametric mode, we're not really using theta like when I showed you how to use the function mode to get your table of values. We're just going to put t in here. 2 sine of t, sine of t. Remember, variables are completely arbitrary. So here I got 2 sine of, well, easiest way, just hit the independent variable button. Cosine of t, 2 sine of t times sine of t. I guess some people really get annoyed that I don't put those closing parentheses on there. All right. I'm just going to go to zoom 6 because I think that's going to cover it. Hey, look at that. That is, in case you didn't recognize it, that's the first function that we graphed in polar mode today. Look at that. Looks exactly the same. You might not be happy that it's a little bit football-y instead of circle, so you can just go into zoom and hit square. And you'll see it actually looks perfectly circular. Right. But hey, that's not the easiest way to graph it. The easiest way to graph this is to go into polar mode. So back here, when we were in the mode, we can actually, instead of selecting parametric, we select polar. And if we were in class, I would let you guys just play with your calculators and see the stuff, but I'm just going to guide you through it here. I'm going to point out that here, now we've got R1 equals blankety blank blank blank. So in this case, if we wanted to do the one that we were just doing, we've got 2 sine of, look at that. I just hit the independent variable button, and up pops a theta. Makes it really easy to type it in there. Before I hit graph, I'm just going to show you window. Looks similar to when we were in parametric mode, except instead of Tmin and Tmax, you got theta min, theta max, and theta step. I'll come back to theta step to really mess with these graphs and make them look really bad. And zoom, all the same stuff. If I go down to zoom standard, I'm going to get that perfect graph right there. And just to point out here, zoom standard makes your theta min 0, your theta max to 2 pi. You don't always need to go up to 2 pi, and sometimes you do need to go beyond 2 pi to get one iteration of the curve. But 2 pi is generally a good place to start with because of the periodicness of sine and cosine, which is really what we're going to be dealing with here. Other stuff that we got here, trace looks exactly the same. Your table, if you go to your table, you now have theta and r. If you go to calculate, you lose a lot of functionality on there. All right. So now, you guys know how to graph a lot more easily. And to be honest with you, if you were graphing this, I would be all right with you just going to your calculator, saying 1 minus 2 cosine of theta, hit graph, and there you have the limacon with the inner loop on that. And just to point some things out to you guys, you can adjust your window so you can see it going a little bit better. You can see that it looks like the max is 2, min is 2, and down to -3. So I might go -3 up to 1, -2 up to 2. You can just see that limacon a little bit better. That just looks nice. Another thing to point out here is, in order to find out how far up you need to go to traverse this curve exactly once, you can go to trace, pulls up that particle, and if you hit right, it just advances it in the upward direction for the theta, and just goes all the way around this curve, and you're looking for where it ends up at that point again. And when you end up at that point, that is one iteration of the curve. So you can see here your theta is now 6.28, and that's 2 pi. So you're going to have to play around with that. I know on the homework tonight it does ask you how far do you have to go through one iteration of this curve. All right. Well, there's an exploration that I asked you guys to do. You can do that if you want. But what I really want to get on to is the names of all of these polar curves and what happens. Like, I'm going to guide you through graphing these polar curves, because you'll have to do that on your homework tonight. And honestly, we're all right with you guys just graphing it in your calculator and copying it off your calculator. So the first type of function that can occur is something called a Dirichlet. Again, right up here, Dirichlet. All right. So to get a Dirichlet, the 3 different ways that you can do this: you can have r equaling any constant, you can have r equaling a sine of theta, or r equaling a cosine of theta. We graphed both of these types of functions before. This one's just like kind of obvious because you have r equals a constant. That just means no matter where you rotate, you're at that same point. So you have the collection of points that are equidistant from the pole, and that equidistant point is that distance is the r. So if we had like r equals 5, for instance, I can go over to my calculator and I can see if I've got r equals 5, zoom standard, yeah, that's a circle. If you're bothered by the circle not being exactly square, hit zoom square and boom, you got it. So that radius, that r, is your radius on the circle. Now in these ones, a is any number you want. It could be positive, it could be negative. Let's say we've got r equals, let's go with 5 again. 5 sine of theta, or r equals -5 sine of theta. These are 2 different graphs that I'm going to graph here. All right. So the first one I've got is 5 sine of theta. Unsurprisingly, we already did that. It's a circle straddling the y-axis above the x-axis here. Now if I go in here and just pop in a negative in front of there, same thing, but it's below the x-axis. All right. Something to, oh, actually, another nice thing to point out here is that a value is actually the diameter of the circle. 1, 2, 3, 4, 5. Yeah, see that? So the radius will be half of a. It's the same thing on a cosine of theta, but notice the difference between these two. This one straddles the y-axis, this one straddles the x-axis. If you don't know what I mean by straddles the axis, figure it out, okay? Let's say we've got r equals, oh man, I don't feel like doing 6. There we go. 6 cosine of theta, or r equals -6 cosine of theta. And again, I'm just making these functions up to fit the format here. So here I would have 6 cosine theta. Yeah, see, circle has a diameter of 6. Again, that's the a value, so the radius is half of 6. And straddles the x-axis. If I put the negative just pops it to the other side. All right? So that's something important. If you see this format, it's going to be a circle. The graph will be a circle. Next format we have is something really pretty. It's called a rose curve. Next Valentine's Day, borrow 11 calculators because you have one. Make a rose curve on each one and give it to your boo. He or she will be appreciative of the dozen roses that you got. Dad joke. All right, cool. So rose curves are always in the format of a sine or cosine of a number times theta. The sine or the cosine determines what axis you're going to straddle for this. So like you can see some of these have just one axis of symmetry. Some of them have biaxial symmetry. If you have one axis of symmetry, if you have sine, it's going to straddle the y-axis. If you have cosine, it's going to straddle the x-axis. Really don't need to know this, but you know it's fun stuff to know here. If you have biaxial symmetry, two axes of symmetry, and you have sine, the axes are not going to split the petals. If you have cosine, the axes are going to split the petals. The A here actually determines the radius of the maximal radius on this function, and the N determines the number of petals. The higher the N, the more petals you have. If N is odd, that means you're going to have an odd number of petals, and it's the same number of petals. If N is even, that means you are going to have an even number of petals, and it's twice whatever N is. So like, for example, let's say I have R is equal to 2 sine of an odd number, oh my gosh, 3 theta. That's going to be a 3-petaled rose curve with a maximal radius of 2, and it's going to straddle the y-axis. It's basically going to look exactly like that. And just to prove to you that I know what I'm talking about, 2 sine of 3 theta, boom, there you go. It's kind of tiny, you can't really see it that well, but you know, whatever. Let's say instead of using 3, I would use 4. That one. Do I want to do 4? Do I want to do 4 yet? Yeah, let's do 4. All right, let's make it a little bit bigger so that I can fill out my my graphing calculator here. Let's make it 6 sine of 4 theta. All right. So here we've got 6 sine of 4 theta. Okay, cool. You can actually see 1, 2, 3, 4, 5, 6, 7, 8 petals. It is straddling. Why do I keep modeling these? It's straddling the x and the y-axis such that neither axis splits the petals in half. What you might notice about this curve is it's really not smooth. I think I told you guys that the smoothness in this in these curves is essential. So what actually happens here is back in the window, you can see the theta min is 0, theta max is 6.2 2 pi here again. The theta step is really what's causing that jaggedness on there. And whoopsies, that was at 0. Okay. If I make my theta step smaller, that means I'm taking fewer movements from each theta to produce the next theta, and the fewer movements I make, the better the curve's going to be. So I can see, to make that 0.01, this curve is a lot smoother, different by a factor of 10 there. But what happens there takes a lot longer to graph. So if you get jaggedness out of your curve, you might want to go in and change your theta step. Right now, I don't care about that, so I'm going to keep it as jagged as possible, and let's go back to some zoom square so it looks nice. If I wanted to check out what the domain of this function for one iteration, again, I'm looking for where does it come out like that. All right. I want to see where it traverses all 8 of the petals, and I can see after that full option, it has traversed all 8 of those petals. Versus if I have R equals 6 cosine of 5 theta, notice that the domain for the uniqueness of this one is from 0 to pi. 6 cosine of 5 theta. Again, jagged, but I don't care about that. I'm going to go to my trace, and I'm going to figure out where it goes back to that. So I'm going to traverse it. Okay, so there's 3 petals, 4 petals, 5 petals, and I've gone through my 5 petals there, and I'm back at the original starting location. That was 3.14. So you can actually see the domain for one unique iteration of this rose curve is from 0 to pi. And just for funsies, let's make r equals, let's keep it at 6 so that we can see it. 6 cosine, let's go something ridiculous, 12 theta. So just to point out here, n is 12. Since n is even, I'm going to have 2 times 12 petals. I'm going to have 24 petals on this. Okay, 6 cosine of 12 theta. Yoinks! Yoinks a doinks. So you can see, I don't even see the petals on that because my resolution is so low on there. If I go to my theta step and again make it 0.01, I'm going to think, okay, yeah. Again, making my theta step smaller produces smoother curves. Downfall to that, takes for frickin' ever to graph. About 10 times as long to graph this as the standard viewing window. All right, so those are rose curves. Next one we have is a nice French word. So those of you that speak French maybe recognize this word. I don't know your life. So I looked this up a few years ago, and limaçon apparently is Old French for snail, and somebody thought these looked like snails, so they call it a snail curve. What do you know? You got the limaçon with inner loop. It looks like this. That's what we graphed before. You've got a cardioid. It looks like a heart, hence the base of card. Dimpled limaçon, where it kind of looks like it's a circle with a dimple in it. You got a convex limaçon. A convex limaçon is like I know it looks like a circle, but really it's more like a circle, a basketball that's gotten a little bit flat, so it's a little bit flatter over here. And just to point out, these are always in the format of like a plus b sine of theta, where a and b are any numbers that are bigger than 0, or r equals a plus or minus b cosine of theta. Notice there's no number, there's no multiple inside of the trig function. It's out in front of the trig function. The same standard of the axial symmetry stands from the circles. So if you have a sine, that's y-axis symmetry. If you have a cosine, that's x-axis symmetry. So just looking down here, this would be some sort of limaçon curve where you had a sine involved with it. You can actually figure out which type of limaçon curve it is by comparing a to b. So like in this case, a to b is smaller than 1. That means that a is smaller than b. All right? So in this case, if I wanted to make a limaçon with an inner loop, I could have r is equal to, I'm going to make it a sine so that it matches up this one. Again, we want a to be smaller than b, so let's make this 3 plus 4 cosine of theta. All right. And real deal, these functions are so complicated to graph, I am not graphing them by hand. No chance, no how, no way. Make the graph a little bit faster. So you can see I have that inner loop in there. Why did I use cosine? I meant to use sine so that it would match that. I even said that out loud. If I change it to sine, you can see now it straddles the y-axis and it matches that curve right there. If I wanted to change that from a plus to a minus, same thing as with the circles. It just flips it over that x-axis or the y-axis if it was the cosine. So just to be clear, that cosine one. Yeah, there you go. Cardioid, that means the ratio of a to b is equal to 1. Yeah. Oh, there's actually a nice little application to this one. If you're into sound or anything like that, that's the best I can do for drawing a microphone. There's something called a cardioid microphone. I learned this a couple of years ago. And a cardioid microphone is so named because if you stand in front of, or if you stand near the microphone, the place where you can pick up sound is actually modeled by this cardioid. So if this microphone is right here, it's a cardioid microphone. If I stand within this cardioid, the microphone's going to pick me up. So again, ratio of a to b is equal to 1. So that's just going to mean r equals, let's go 3, minus 3 sine of theta. Again, it's not going to match that because this is sine. That's got x-axis symmetry, so obviously it's a cosine. But look in here, I got 3 minus 3 sine of theta. And look at that. It's a nice little heart there. I wear my cardioid on my sleeve. And just to, again, emphasize that domain here, I'm just figuring out where am I going to get back to that. So going through, back at that point after 2 pi. Versus the dimpled lemniscate, where I've got the ratio of A to B is between 1 and 2, so A is now bigger, but it's less than twice as big as 2. Alright, so I could have R equals A bigger, so 3 minus 2, let's go sine again, sine of theta. I'm betting that's going to look similar to this. Again, A is bigger than B, but not twice as big. So here, I would have 3 minus 2 sine of theta. And you can see it's just a little bit less pronounced there. Got a nice dimple. And here, if I trace, when I go around, the first time I go around, that's 6.2. Oh, I guess this is wrong then. The domain is from 0 to 2 pi. Oh, from 0 to pi. In convex lemniscate, that just means A is bigger than twice as big as B. So like maybe R equals 4 plus 1 cosine of theta. 4 times as big. 4 plus, I guess we don't need the 1 cosine of theta. And you can see there's that convex lemniscate right there. Again, I don't really recognize these when I just look at them. That's a lie. I do now, but that's just because I've played with them for so long. Lemniscate curves, you might also know it as that funny infinity symbol. Next time you see somebody with a cute tattoo on the inside of their wrist and it's an infinity symbol, go up to them and say, hey, sick lemniscate, and watch how dumb they are. Because anytime you tattoo anything on your body, you should know what it is. But anyway, lemniscate curves are in the format of r squared equals a squared sine of 2 theta, or r squared equals a squared cosine of 2 theta. Just looking at that, I might have like r squared equals, let's take a number 3, square it, we get 9 sine of 2 theta. Bad part here is now I've got r squared, so in order to solve this for r, I have to square root, which is going to be r equals the square root of 9 sine of 2 theta, but I know some of you people are remembering that when we take a square root in an equation, we need to make it plus or minus. So if I was to graph this function, I would actually have to graph it as the square root of 9 sine of 2 theta. And then in the second R2, I would have to put negative square root of 9 sine of 2 theta. Those of you who have me know that when you have an TI-84, you can hit alpha trace and just pull up R1 right there. And there you go. There's that lemniscate. Right? You'd have to do the same thing if it was a cosine. Just to be clear, you probably saw that the blue and the red graphed on top of each other. That's just indicating that they produce the same graph. If I was to go to trace, I could actually go around one iteration of the curve. What? One iteration of the curve gets me... Oh, yeah, that's right. Okay, it's the negatives in there. Alright, so you can't have those negatives busting out. But it does get us through in pi. Alright, and the last one. It's called a spiral of Archimedes. It's really difficult to graph. Spiral of Archimedes is just r equals theta for theta greater than 0. What I like to do with this one, it's actually super easy to graph. R equals theta, and hit graph. It's actually uninteresting when you just go from 0 to 2 pi, because it just goes in that little circle right there. What I'm going to do right now, I'm going to make my theta max go up to a hundo. Alright? I'm going to make my x min negative 100. My x max positive 100. And same thing for y min and y max. Just so you guys can see what the spiral of Archimedes looks like. And Wait. Let's change that scale to 10 so we don't see all those tick marks. And now you can see the spiral filling it out. It's dizzying, way dizzying. Kind of looks like a thumbprint, doesn't it? So you can really appreciate the spiral of Archimedes when you make it go a little bit bigger like that. And what I find to be super fun, let's actually make this go up to 300 so that it can fill out the whole thing. I'm going to change my theta step. This next thing that I'm doing is bad. Never do this, ever, unless you're trying to have fun. Change your theta step to something like 2. That means you start at 0 radians, you go up to 2 radians, then 4 radians, then 5 radians, and no surprise, you get a really bad graph. You mess with that, make it 1.5. I think the biggest you can make it is like 7. You just get some really funky graphs. They are wrong. They're absolutely wrong. Never trust these as like good graphs. Like that, obviously, is just horrid. I think 3 is a fun one. Yeah, you can mess with these. Just get some like really funky looking graphs. It's just fun to mess around with. I could do this all day. Again, changing your theta step to something big like that is just bad. You should never do that. That's what it should look like. It should always look smooth. Anytime you see corners in polar graphs, that's bad news. Corners are bad in polar. Here's your assignment. Try 23 and 25 by hand. They're not uber difficult. 38 through 58, those are going to be using your graphing utility. Graphing utility is a calculator. If you are using Desmos, all you got to do when you type it in, you can type in R equals and literally type in theta, Theta, if you're using a computer, and I'll type it in there. I believe on the phone there is a button for theta. All right, I'm out.